Okay, great. So welcome everyone to our first plenary talk of week 2, our third plenary talk overall. We are really delighted to have Arunima Ray here to tell us about embedding surface and 4 manifolds. Dr. Ray received her PhD from Rice University in 2014, where she was advised by Tim Cochran. After a postdoctoral appointment at Brandeis University, she joined the Max Planck Institute in Bonn, Germany in 2017, where she is now a Lisa Meitner group leader. She is an editor of the forthcoming book, The Disk Embedding Theorem, which details Friedman's proof of the topological Poincare conjecture in dimension 4. And we're really glad to have her today telling us about embedding surfaces in 4 manifolds. So during the talk, feel free to unmute and ask questions as they come up. Just like last Thursday and Tuesday, I guess, at the end of the talk, we will have a question and answer period, and we will ask you to use the raise hands feature, which is down in reactions for the question and answer period. And feel free to message any of the organizers who are the co-hosts if you have any questions about technical details during the talk. Okay, with that, thank you very much for being here, and Aru, take it away.
Thanks, Allison. Thanks to everyone for being here. Welcome to my office. It's a pleasure to see all of you out there. I do want to say I have a 2-screen setup, so if you turn on your camera, that would be super helpful for me. I think it doesn't get recorded. It's just helpful for me to see expressions, to see how things are going over. I have to say, like, it's been ages since I've seen lots of faces in person, so it makes for a nice change. Anyway, all right, so let's get started. So the goal for today is to talk about embedding surfaces in 4 manifolds, like Allison said. And the sort of question, the motivating question for this whole talk is this one. Suppose you have a map of a surface into a 4 manifold. I would like to know when it's homotopic to an embedding. And so this is a sort of question, when you see something like that, maybe the first thing that comes to your mind will be, well, can I do some sort of perturbation or something to make sure that things become embedded sort of generically? So for example, if you have maps of one-dimensional like circles into a surface, generically they do intersect and you can't push that apart. On the other hand, if you have a map of a circle into a 3 manifold with that extra dimension, then in fact you can push things apart so that things become embedded. So in the case of a 4 manifold, if I were thinking of a map of a circle inside of a 4 manifold, that would just be generically embedded because I can just I have enough dimensions so that they don't intersect anymore. And similarly, if I had a surface and a circle, they wouldn't necessarily intersect because I can just push those apart with that last 4th dimension. But in the case of a surface, because 2 plus 2 is equal to 4, I can't just push things apart and make things disjoint or embedded just by using sort of a big powerful theorem. So here, generically, a map of a surface into a 4 manifold has isolated double point singularities and this is coming from the fact that 2 plus 2 is equal to 4. And so using sort of these powerful theorems, this is the most that you can do. You can make sure to perturb things, but then you'll still have these double point singularities that you can't just get rid of. And so it's a bit unusual, maybe, to think about surfaces intersecting in 4-dimensional spaces. So I thought that I would start off by describing how we like to think about this sort of thing, just to get us all on the same page. So there are 2 ways in which we like to do this. So there's the top way and the bottom way. So let's start with the top one. So I'm going to think of a 4-dimensional space, sort of locally. So locally, a 4 manifold will look like R4. And so I'm going to think about that R4 as R3 times a time coordinate. And that time coordinate is what's written down here. And so what I'm looking at right now, if I think about this R4 region, I want to think about this blue surface, the one in the central panel here. This is sort of like the XY plane. And so that's why it shows up at time equal to 0. It's in that central time slice. And these red lines that we have over here, these vertical ones, these are tracing out the z times time coordinate as I move sort of backwards and forwards. Does that sort of make sense? So you're supposed to picture in your mind, you have this red vertical line, and as you move backwards and forwards, that's like a one parameter family of lines, so it's a plane. It's the ZT plane. And the XY and the ZT planes, they're supposed to intersect only in the origin, and they do, that's right there. Okay, how does that sound? So you should think of a movie. It's a movie of R3, it's moving in time. And there are two surfaces. One of those so the picture looks a little bit asymmetric, but that's just because I've chosen this particular format. So one of the surfaces, the blue surface B, shows up as an entire surface in one time slice, but these red lines are drawing out the other surface. The other way to draw this is a bit more symmetric. I just wanted you to see it as well. It's the same idea. I'm thinking of four-dimensional space as a sequence of three-dimensional spaces, but now my surfaces are being pictured in a sort of more symmetric way. So if I focus in on the red lines, it's tracing out a surface again. The blue lines are tracing out a surface, but again, in that middle time slice, I get that single point of intersection. Okay. And so these pictures, I think, just as a comment, we tend to draw just these middle pictures, like the ones where the intersections show up, just because we sort of think in our mind what the other times are supposed to look like. But if you haven't seen these before, that can be a bit confusing. So I wanted to make sure that you sort of, if there's one thing you should take out of this talk, this could be it. Okay, it's like it might look like a schematic, but it's actually extremely precise. You can make things very precise by doing things this way. All right. How's that going so far? Okay. Surface, thumbs up, awesome. This is great, look at, wonderful, thanks for that. Positive feedback, very good. Okay, all right, so this is what it looks like when surfaces intersect in isolated double point singularities. So at each of these singularities, you'll see a picture like this. Let's return to our original question though. So I was asking if you have a map of a surface in a four-dimensional manifold, I would like to know whether it's homotopic to an embedding. So you might say that it's natural to just think of how plentiful are embeddings of manifolds in other manifolds. That's a fine reason to care about this question. I'd like to present a sort of extended example of sort of another reason, one reason why people started to think about this. So let's get started with this example. We'll start off with a nice invariant of four-dimensional manifolds, closed four-dimensional manifolds. If I look at middle dimensional homology, so H2, because of Poincare duality, I have intersection form on that middle dimensional homology H2. And so one way to think about it is that it's coming from the cup product pairing, right? So H2, the dual of that is H upper 2, and you have cup products that land in this top dimensional cohomology, which is just C. That's where that closed came in. And it turns out, because of Poincare duality, this is a unimodular form. Fine. So you can think about this entirely using sort of algebraic topology stuff, which is fine if you prefer that. Personally, I prefer to think a little bit more geometrically. That's just how my mind works. So it turns out, cool fact about four-dimensional manifolds is that elements of H2 can be represented by surfaces, embedded surfaces. that's a related fact, but let me not go into why that's true. But you have surface representatives of these two-dimensional homology classes if they happen to intersect in these isolated double point singularities, as we mentioned. They have signs. Ideally, you count them all up, and that's precisely what that what this intersection form measures. I could go on. I could go on about this, but I won't. Just so we can move forward. But this is a sort of very nice invariant of four-dimensional manifolds. Instead of giving you more details, I'd rather give you some examples. So here, if you consider S2 cross S2, the intersection form looks like this 2x2 matrix. How should you think about this? Let's think about it as an analogy. So you could instead think about S1 cross S1. And in that case, you have these factors. So you have the S1 cross 0 and 0 cross S1 factors, and they intersect at that single point that you're looking at. In S2 cross S2, you will have S2 cross 0 and 0 cross S2, and they'll once again intersect in that common point. So that's not so surprising, and that's precisely what this matrix is saying. These ones on this off diagonal, that corresponds to that point over there. And these zeros, the zeros are kind of nice. The zeros are telling you, for example, if I take this red circle, I can just push it off of itself and get a copy that doesn't intersect the one that I started off with. So that's what that 0 is about. Similarly, if you happen to know, but totally fine if you don't, if you look at the four manifold CP2, its intersection form is 1 by 1, and it just has a 1 in it. Okay. And so then by taking connected sums, you can sort of generate lots of different intersection forms of closed four manifolds. Okay. All right. Does that sound reasonable? Okay. So now I know a way to start with a closed four manifold and get for myself a matrix, a symmetric matrix with integer entries. This says screen broadcasting has stopped. 1 second. Let me try to. Interesting. Okay. Anyone have any questions while I reconnect my tablet? Sorry about this. Meeting passcode, is there one?
Yes, I can give you it.
Awesome, thank you. I assume everyone here knows it already.
It's one of the things where it's embedded in the link, but sometimes maybe it wants additionally anyway.
And if you ever run into this, can you hear me? If you ever run into this again, you can click the little shield in the top left, and it has all the meeting information.
Oh, awesome. That's a good point. Thanks, Miriam. Sorry about that. Just checking that everyone's awake, you know? You know how it goes. Yeah, my apologies. Okay. Now that everyone's awake again, how is everyone doing? Okay, everyone feeling alert? It's just like, okay, great. All right, where were we? We were saying that given a closed four manifold, we now know a way to get an integer matrix, which is unimodular, meaning that it has determinant plus or minus 1 out of that four manifold. And that gives us sort of a natural question to ask, namely, which unimodular symmetric integer matrices are precisely intersection forms? So on the last slide, we saw some of our favorite unimodular matrices. So for example, the identity matrix will come from connected sums of CP2s. Sort of the 0, 1, 1, 0 matrix, that's going to come from S2 cross S2s. We can get any combinations thereof as you like with connected sums. But you might have a different favorite square matrix, such as this one. So this matrix comes out of the E8 lattice. And essentially, the E8 lattice shows up in all sorts of mathematics, most of which I know very little about, so I will not attempt to describe them. But given this lattice, you can write down the adjacency matrix coming from this lattice, and that looks like that thing that's written on the left, assuming I did that right. And if you have a lot of patience, you can compute the determinant and see that it is, in this case, 1. And so a question that you might ask, and many people did ask, is, well, here's a unimodular symmetric integer matrix. Is it the intersection form of a closed four manifold? Or, just like we did for the other matrices, but what about, block sums of this matrix with itself? And it turns out, let me just spoil the answer. The answer is yes, for a topological manifold. But not for any, excuse me. Smooth four manifold. And then here, this is due to Friedman, and this is due to Rocklin and Donaldson. And so dimension 4 is the first dimension in which we see that there's a difference between the topological and smooth categories for four manifolds. And in this is a situation where we can sort of see that difference, that this matrix can only be realized by a topological four manifold, but smoothly we have no hope. So I would like to explain where does this come from? Where is there a place where we need something, where we can't do something smoothly? Where does that fail? So here's sort of a construction of a manifold with one of these forbidden intersection forms. It comes from the K3 surface. K3 surface, lots of people study the K3 surface for lots of reasons. I'm going to give you this description of it. It's a subset of three-dimensional complex projective space, which is the solution of this quartic equation. This is not particularly useful relevant for us at the moment. What is relevant is that this manifold is simply connected, and so that implies that its pi2 is isomorphic to its H2. And we also happen to know that its intersection form of the K3 surface is of this form. It has 2 copies of the E8 matrix from the previous slide, and then 3 copies of this hyperbolic matrix, namely the intersection form of S2 cross S2. Okay. And so what's really cool about this is, well, I have this K3 surface, and suppose I were trying to build a four manifold with intersection form E8 plus E8. Sort of a standard thing that I could try to do then is, well, here's all this extra stuff. I don't like it. I would like to get rid of it. So I would like to do some sort of cancellation. So algebraically, there's a cancellation because I'm looking at it. This has this decomposition as this sum. So that algebra I want to mimic in geometry somehow. That's my goal. So let's sort of I have to stop saying sort of. Let's look at these hyperbolic matrices that we have at the end there. I'm going to just focus on one of them because that will be plenty. In the nicest possible case, well, what is this representing? This is a form on middle dimensional homology, H2, which in this case is pi2. So these correspond to elements of pi2 of K3. So they're represented by maps of S2. Okay, so there are some spheres that are mapping into the K3 surface that correspond to these intersections. Is there a question? All right, so let me sort of draw the ideal situation of what might be happening. So in the ideal situation, I would get a picture like this, which looks like in this case really does sort of look like S2 cross S2. It has these two S2 factors that intersect at a single transverse point. So that's what the algebra is sort of detecting, that there's something like this. However, that is just wishful thinking. In practice, what I have is something different. In practice, I rather have a picture like this, where if I try to maintain the color coding, one of them will be red and one of them will be purple. And so what do I mean by this? Well, maybe I have these canceling pairs of intersections that the algebra does not detect, but does show up in the geometry. And so what I want to know is whether I can pass from the left-hand side to the right-hand side of this diagram. And now you might be wondering, well, why would that be sufficient? Well, the reason I really like this right-hand side of my diagram is if I actually had embedded S2s representing these hyperbolic summands, then I would be able to do surgery to remove that summand from my manifold. So if you happen to know what that is, excellent. If not, here's another analogy. So the thing that I'm asking for us to do in the case of S1 cross S2 would look like this. So I would have, S1 cross S1 would look like this. So if I have something like this, then I could cut along this purple guy and then pull it apart and cap it off with discs. So it would look like this. That's purple, and then there's a red thing around the side. And so the point is that when I have homology classes represented by embedded spheres, then I can do this cutting and pasting operation, namely precisely what I did to go from right to left over there, to just remove that from my manifold. So this is like do surgery. Okay, so what I've been trying to convince you of is that if we could realize this thing that's happening on this right-hand side, we'd be very happy, because we could do this cutting and pasting operation and then remove this thing geometrically from my manifold. So let me just fill out what our goal is. Our goal is to realize algebra by geometry. So if we can accomplish this question mark, well, then we'd be able to remove one of these hyperbolic summands, and if we're really lucky, we'd remove all three of them, and then we'd get a topological manifold realizing. Then we get a manifold realizing E8 plus E8 as an intersection form. Okay. All right. What was the problem? The problem was we had all of those extra intersections that we didn't like. So if we could get rid of all those extraneous intersections, then we'd be very happy. So the question is, how do we do that? What is a way to get rid of these extra intersections that I don't like? So now we can practice our four-dimensional surface visualizing techniques. So here is a very nice situation of two surfaces, the red and the blue one, intersecting in these two extra points. And I've marked them, one with a plus and one with a minus. Okay. And so I would like to get rid of these two extra intersection points. How will I do this? So in this particular case, I see something very nice happening. I see that if I look at this circle that goes along blue and then along red, this loop that I've drawn, this happens to be the boundary of a disk. A super nice disk that has boundary half on red and half on blue. And so given this disk, I can do something, and here's the picture of what I can do. That disk from the previous slide is here in the middle. And what I've done is I've taken two copies of that disk, and I've sort of placed it on top of the blue surface. So some people like to call that the bubble. It's like a bubble. To me, it's like a tea cozy. It's like a little hat that you put on your little surface. Okay, choose your favorite analogy. And then what have we accomplished? Well, these 2 points of intersection are no longer there because, like, you know, this rectangle is no longer, the interior of that rectangle is no longer part of blue. Like, it's been replaced by the tea cozy, right? So these 2 extra points of intersection have gone away. Okay. This is called the Whitney trick. It's a pretty good trick, as tricks go. And so what this sequence of pictures is supposed to convince you of is that if we're able to find embedded Whitney disks, there's in brackets, you have to care about framings a little bit, but we won't for today. Then by using this procedure, you can remove those extra points of intersection. So this is great. This is precisely what we want. Okay. Although you may be wondering, how is this helpful? Because we wanted to embed surfaces, and now you want me to find some embedded disks. So it seems like the same question. So what's going on with that? We will come to that, but it's a valid question to be asking. Okay, so when can we find Whitney disks? Well, it turns out that there are some algebraic obstructions to finding them. And so these are intersections again, but now they're counted with a bit more generality. Now we're going to count them in the group ring of the fundamental group. So let me sort of describe that. Let me actually describe that. So you have, in this case, there are these spheres that are F and G, and they intersect at some points, including P. And I would like to describe to you how to compute this quantity lambda. Here's how this works. I'm going to start off with some arcs that join the base point of the four manifold to the spheres F and G. And then I want something that corresponds to that point of intersection P. I would like an element of the fundamental group. Well, I'm staring at one right now in the face. I should start at the base point, go to F along this arc, go to P, go to this arc, and then back. So that is a perfectly fine element of the fundamental group at that base point. Let me call that gamma of P. And this lambda F and G is going to be the sum over all intersections of F and G of these curves gamma of P, and then there's a sign. I won't go into where that sign comes from, but assuming you're in an orientable manifold, you always get a sign like this, and it's not too bad. And then this element is well-defined for F and G simply connected. And so let me just point out that it is well-defined modulo the choices of these arcs. Okay. The thing that we'll really care about, though, is when this quantity is 0. So let's think about how that works. So we're counting something in the group ring of the fundamental group. So when is this sum going to be 0? Well, all of these contributions have to cancel out in pairs. And so in this particular picture, P, the contribution of P looks like this, whereas the contribution of this other point looks like this. And so what's the difference between those two things that I just drew? It's this circle in the middle there. And so the contributions of these 2 points of intersections, they're going to cancel out precisely if this circle is null homotopic in the four manifold. Okay. And what does it mean to be null homotopic? It means that there's some disk that's the bound that has that circle as boundary. Okay. And so let me just summarize. Lambda of F and G is equal to 0 precisely if all points in the intersection of F and G are paired by immersed Whitney disks, just meaning that they're not embedded with the right sort of boundaries. So they're framed, disjoint, embedded boundaries.
Aru?
Mm-hmm.
Can I ask a technical question here?
Sure.
I guess from my understanding of these, I thought you had to mod out by something else, like reversing orientation or something, like the group ring is, can you remove that condition? Is that, am I remembering?
That's a great question. So I was going to just avoid talking about this.
Okay,
So
I'm sorry, but the point
no,
is,
no, you're totally fine. So let me sort of answer you in a riddle. So in this case, where F and G are in a particular order, you don't have to mod out by anything. You can just land in the group ring. But when you're thinking about the self-intersection number, so in the case of a self-intersection, your picture would look like this. So you have, let's say, here's that point of intersection, the self-intersection, and then this is not much of a riddle. You can go to that point of intersection either from the left or from the right, and you have to make a choice of which direction comes first. Yeah. And so when you're talking about the self-intersection, you don't land in z pi 1 of m, you have to mod out by this choice of which way do you start. Okay, so that's the not as riddly answer.
Thank you.
But it's a great question. Let me ignore that point though, and say that there is something called the self-intersection number of f, and vanishing of that means that all the points of self-intersection are paired by a generic collection of Whitney disks, which, when you weren't looking, I named this sort of thing that we had up top. And then similarly, it turns out that algebraically dual is what we call it when two surfaces intersect precisely once, and that means that all but one point in these intersections are so paired, and that's meant to be the algebraic analog of being geometrically dual, which happens when there's precisely one point of intersection. Okay, all right. How am I doing on time? It must be horribly late.
We started at 5 or 6 past the hour.
Okay. All right. That's actually not as bad as my usual, just to scare everyone. Okay. All right. I mean, yeah. How does all of this sound? This is saying that there were some details over here, but here's the top line view. There is an algebraic way to sort of detect whether it's even possible to find some Whitney disks. Okay. So this is saying if this lambda and mu, they vanish, that means there's no algebraic, there's no homotopic obstruction to finding a Whitney disk. So what we really want is to find an embedded Whitney disk, but first you want to make sure that these circles are null homotopic. And so this is telling you, okay, you're good, you're not totally out of luck. Okay, so there's this algebra. This is the thing that we want to realize by geometry in this case. One really awesome fact is that to implement this strategy in high dimensions, it's not that you would have to try to embed high dimensional disks. Even in super high dimensions, like dimension a billion, you would still only have to think about two-dimensional disks. So you would look at half-billion dimensional submanifolds, and they would intersect in isolated double points. But you would still only need a two-dimensional thing to guide this moving apart business. And so what's really cool is that 2 + 2 is not a billion. And so as a result, in high dimensions, you can just always do the Whitney trick. And that's super, super helpful. And so what that means is you can always find these embedded Whitney disks. The only thing that obstructs you is the algebra. So the algebra is realized by geometry. This leads to things like the H-cobordism theorem, if you happen to have heard of this. This is by Smale. So in particular, this leads to the PL Poincare conjecture in high dimensions. By the way, it does not lead to the smooth Poincare conjecture in all dimensions. And if you'd like to know more about that, you could look up the postcard of Mark Powell, which I think is the only postcard without any pictures. So something to really look forward to. On the other hand, where does Whitney come into this? Whitney used this to prove his embedding theorem. So that uses this same idea. It also leads to things like surgery theory and so on. So a motto of this is whenever you think that, oh, high dimensional manifolds are fine, we can sort of work with them, behind the scenes, there's a lot of applications of the Whitney trick that are going on. So it's super, super helpful. Well, that's high dimensions. By high dimensions, I mean bigger than or equal to 5. What about dimension 4? So in dimension 4, I still have the problem that 2 plus 2 is equal to 4. So what can we do about this? Turns out that nonetheless, even though 2 plus 2 is 4, we can't change that fact. We can sometimes embed disks. So this is really cool. And this is precisely the thing that distinguishes between the smooth and the topological categories. So all of these embedding things that we wanted to do, these finding of embedded Whitney disks, all of that, we can do topologically, but not smoothly. All right, so let's look at this theorem. Let me first go through what it's talking about. So we're going to start with a topological manifold M. There's a restriction on its fundamental group, which I'll talk about in a second. For the moment, you could think about a simply connected four manifold, and that's perfectly fine and already pretty cool. We start off with a compact surface. It has some number of components, but we're going to assume that each of the components is simply connected. So that means that sigma I is either D2 or S2. That's what I'm assuming at the moment. And then I'm going to start off with a function f. So f is the union of some number of fi's, where each fi is a map on sigma I. I'm going to assume it's an immersion, meaning that it has these isolated double points. So it has these double points of this form. And then there are these conditions. I'm hoping that you should think about this as sort of the algebra that you're trying to approximate. So I'm requiring that these algebraic intersection numbers vanish. And so what that means is that so lambda of fi fj and mu of fi, these are all 0. So up to algebra, the components of sigma, they don't intersect one another. And then there's this additional condition of there exist some other spheres, helper spheres, sort of auxiliary, that pair nicely with the f's. So just a reminder, this means that the intersections of the fi's and gj's, these are like the Kronecker delta. Okay, so that's a lot about the hypotheses. Here's the way you should think about this. Here's sort of the algebra. Algebraically, there's no obstruction to there being an embedding. So all sorts of immersed Whitney disks are available to you. And what the disk embedding theorem tells you is that, well, in that situation, you in fact have the ability to homotope that map F into an embedding, F bar. And then additionally, these embeddings have geometrically dual spheres. So I had this algebraic input, so algebraically up to intersection numbers, I had a sphere that intersected F precisely once, according to this Kronecker delta function. And then in the output, I actually get the geometry. So again, the motto is that here are the algebraic input, and then the theorem tells you you can realize this. geometrically. All right, so let me write down some attributions for this. So this was proved based on constructions of Casson. The breakthrough was by Friedman in 1982, and then this was improved by Friedman and Quinn in 1990, and then this last part for fundamental group not equal to 1, this is due to Mark, Paul, myself, and Peter Teichner. Last year, this year, something like that. Okay. All right. So I'm going to say a little bit more about the statement of this theorem in a second. But how does this sound sort of overall? You should be thinking about this as here's the algebraic input. And in this particular case, I can in fact realize it geometrically. Okay. All right. I have about 5 minutes left, I'm aware, and I think we can do this. We got this. Okay. Quick comment, I didn't talk about what locally flat means. So you should think about that as it has a nice normal bundle neighborhood. Okay. So just like a smooth embedding would have a nice normal bundle, locally flat embedding has the same property, but only in a topological sense. Happy to discuss that more at the end. Okay, so the disk embedding theorem is super cool. What are some reasons? What are some ways to see this? Well, many of the things that I mentioned in high dimensions now hold in dimension 4, just in the topological category. So in particular, you get the topological H-cobordism theorem. You also get the S-cobordism theorem when you have a good fundamental group that works. I mentioned the surgery sequence. The surgery sequence is defined and exact. Again, for good fundamental groups. So that's really cool. And then, these were proved by Mike Friedman, but then you also, Frank Quinn came along and he expanded upon this quite a bit. So he proved the annulus theorem. So he proved this really cool fact. And one of the amazing consequences of this is that connected sum of topological four manifolds is well defined. And that may be one of the things that you never knew you had to worry about. But good news, you don't have to worry about it, but only because Frank Quinn came along and proved this theorem. He also proved, by the way, at the very beginning when I talked about the intersection form and I said, oh, you take these surfaces and you perturb them so they intersect in isolated double points, is using something called transversality. And the fact that you can do that sort of transversality in dimension 4 also follows from this result. And so in particular, did not know that before. So there's a whole litany of consequences of the disk embedding theorem that are just fundamental to virtually anything you ever want to do with topological four manifolds. So there's a lot there. All right, so I promised I would say something about good groups, so let me do that. So good groups, there's many of them. For example, finite groups, abelian groups, solvable groups. They're all abelian, they're all good. Groups of sub-exponential growth are good. This is due to Friedman and Teichner, Hirschkel and Quinn. They're closed under subgroups, quotients, extensions. However, we don't know whether all groups are good. For example, it's open if Z star Z is good. I would say this is a pretty major open question in this area. Any advance in this would be pretty amazing. For example, one conjecture is amenable groups being good. That's the next step up from sub-exponential growth. We don't know that. Based on by the properties that I mentioned there, if we knew that this group is good, we would know that all groups are good, but we don't. I will notably not tell you the definition of a good group unless someone asks at the end, but maybe worth noting is the definition is purely smooth. There's nothing topological in the definition. It is a strange definition, though. It is not a good definition, but you know. All right, so I'm kind of gonna stop talking about the disk embedding theorem right now, but if you would like to know more about the disk embedding theorem, you could go read this book that is appearing next month, which was written by me plus 11 plus 19 of my closest friends in a very large joint project. Many of these authors are in the audience. Feel free to pester them or ask them in a non-pestering way. That's also allowed. All right. That brings us back to this theorem. How do you feel about the statement of the disk embedding theorem? It's a pretty cool theorem. Okay, I know I have a minute, so let me put my minute to good use. I would like to improve this theorem. Here's how I'll do it. I would like to make this into a surface embedding theorem. And I'll add some extra names. The first name is Stong 94, and then, well, did not leave enough room for us. So this is Kasperovsky, Powell, myself, and Teichner. Coming very soon, coming out super soon. Okay, so what are the improvements that we're going to make? The first thing is I'm going to remove this condition. So we no longer require this to be simply connected. So any old surface will do. By the way, I was thinking about this during Priyam's talk. The only adjective that's in there is compact. So that's no Loch Ness monsters in today's talk, sadly. But actually, the only thing we need is that there should be finitely many intersections. So you could have the Loch Ness monster if it only hits itself finitely many times. That's the main point. Sorry. All right. What else are we going to do? We're going to remove this condition as well. And then the conclusion remains the same. We're going to be able to homotope this map F to an embedding. Again, it's locally flat. But now there's a new invariant that comes out if and only if the Kerr-Vera-Milnor invariant of this surface, of this map F, this is an element of Z mod 2Z, this thing has to vanish. Okay, so this is the surface embedding theorem. I am extremely out of time, so let me do this. Thank you.
Thank you. Let's all thank Aru for her